Get started. Good evening. My name is Barrett Jones, and tonight's webinar is the basic concepts of sound. And what this really is, it's a half hour where I'm going to talk about some basic concepts in the physics and the science of sound. This comes out of work that I've done teaching at a local museum. And the request came from the director to come up with a little bit of science to add to my music education. Um, if you have listened to my previous webinars, you know that I run a music workshop called DC Beat Club, and it travels around to museums and schools, libraries, to bring synthesizers to kids to introduce them to making music and playing music together. Uh, and normally the emphasis with Beat Club is on simply creating beats and bass lines and things like that. But uh, a lot of times educators have asked for some basic sound science principles to be incorporated into um, the curriculum. So I've taken together what I've done for some classes and put it into this webinar. And what this is meant to do is, if you're an educator, it's some quick and easy descriptions of some basic principles involving sound. So it's to give you sort of a something to teach off of if you're teaching um, kids, uh, middle school, high school students. Um, and the other audience for this is if you are um, a student and you have been asked to um, get an overview of some basic concepts of how sound works and basically ways to describe sound. So that's what this is tonight. And we're going to talk about a few um, sort of principles. Of course, there's many different disciplines that involve sound, and there are entire courses, college degrees, advanced degrees on the physics of sound, and of course we don't have time to cover all those tonight. But what I tried to do is cover some things that come up not only with when one is working with sound, but also when one is using synthesizers and pieces of uh, digital equipment or using software on computers. And sometimes you see references to frequency or harmonics or other things, and this is just to put all that into context. So we'll start out today's webinar with talking about sound waves. Then we'll talk about the concept of frequency. We'll talk about harmonics, amplitude, and then we'll sum up what we've covered. So let's just jump right in, no pun intended, to sound waves. So sound travels in waves, just like waves in water. The scientific definition of sound waves are they are a mechanical wave. Um, Here's an example of a sound wave. As you can see, there are peaks and there are valleys, and it's basically moving across a baseline. Uh, some descriptions or definitions of sound waves. Sound waves are a vibration that displaces the particles of a medium. The medium could be air, water, metal, wood, etc. Normally, we think of sound traveling through air, and that's the way that we can hear. Although if you're ever underwater, like in a pool where they're piping in music, you know that you can also hear sound underwater. Sound travels through all types of mediums. Um, so sound is a vibration, and the vibration of sound moves particles, and as the particles are moved by the vibration, they create a wave. So the wave is actually the particles of the medium, the particles of air, the particles of wood, the particles of water that are being moved by the vibration. And this vibration is moving in the form of a wave. So in air, in dry air at 68 degrees Fahrenheit, the speed of sound is 1,126 feet per second, or 1 mile in 4.689 seconds. So that's the speed of sound, and of course there are, when you think about supersonic jets breaking the sound barrier, you know, for example, that when a jet breaks goes faster than the speed of sound, then a distortion occurs and you hear what's called a sonic boom. There's all kinds of different types of sound waves. For tonight, we're talking about sound waves in terms of music. And so here, example A is the sound wave from a musical note. But sample B is also a sound wave, which is noise. So you can see right off the bat the difference between a a sound wave from a musical instrument and the sound wave from something like a jackhammer or a passing car. I want to show this video, which is a really interesting experiment. It's called a Chladni plate, and it's a way of showing what sound waves look like. This is actually a video that is done by a lab at Harvard. So let's see if we can take a look with this. Chladni plates. This is a commonly used apparatus for illustrating what sound waves look like. Check it out. Notice how as he's drawing the bow across the plate, the sand is moving into different forms depending on the pitch of the bow. You can see there the sand on the plate moves to show what the sound waves actually look like. The video is running a little slow, so let's move on. But I highly recommend going on to YouTube, typing in Chladni plates, and seeing some of the demonstrations of how it works. It's quite amazing. For purposes of the basic discussion of sound waves, we'll talk about the sort of common sound waves. The most common sound wave is a sine wave. Other commonly found waves, especially with synthesizers, are a triangle wave, sawtooth wave, and a square wave. Let's listen to these different types of sound waves. Here's a sine wave. Now let's listen to a square wave. listen to a triangle wave. It's very faint. And then let's listen to the sawtooth wave. So you can hear the subtle differences between these types of sound waves. A sine wave is what acoustic or analog instruments produce. Once again, to remind you of a sine wave, and that's what a sine wave, this squiggly line is what a sine wave looks like. And so sine waves are very common, and all acoustic instruments produce sine waves. So that's a quick overview of sound waves. Let's talk about frequency now. And here's a diagram to take a look at. And as you can see, on the left axis is pressure and then time. You can see that baseline, and then you can see the length of a cycle. And a cycle is when a particle moves from its starting point to the maximum displacement distance in one direction. That would be the very top here of that first wave, back to the starting point, which is the horizontal line, and then to the maximum displacement distance in the other direction, which now is the bottom of that wave. So if you look at that first wave, the cycle is what essentially that purple bracket is showing. That is one cycle. So that's one cycle and a frequency. And the pressure is the vibration that is creating the wave. So some different things to think about in terms of frequency. The number of cycles completed by a wave in 1 second is considered the frequency of the vibration. So looking at this previous screen, think about the number of these cycles that happened over the course of a second is the frequency of the vibration. The more cycles there are, the higher the frequency. And so in the terms of music, although scientifically it's not entirely correct to say, but in terms of this webinar and what we talk about, frequency equals pitch. The reason why I'm saying pitch is a perceived property, not objective measurement, is there's a lot of what's called psychoacoustic processes that happen with the human ear and the perception of frequencies. And pitch is really our perception of frequencies. It's not really a scientific principle, it's a musical principle. Here's a diagram of what different pitches of frequency look like. You can see that the low pitch is has a lower frequency of the waves. The higher pitch has increased frequency of the waves. So one cycle, and we're going back here, we're thinking, remember that the number of cycles completed in 1 second is the frequency. So one cycle in this term is called 1 hertz. And 1,000 hertz is equal to 1 kilohertz. The human ear can hear anywhere from 16 hertz to 20,000 hertz. And hertz is named after the gentleman who made this discovery back in the 1800s, Heinrich Hertz. So one cycle is equal to 1 hertz. So from now on, we'll be talking about, when we talk about frequency, we'll be talking about hertz. We won't call it cycle, we'll call it hertz. A440, or A4, which is a note on a musical scale, has a frequency of 440 hertz. A4 is a musical note A above the middle C and serves as a general tuning standard for musical pitch. It's sometimes referred to as concert pitch or concert A. Not so important that you really know all the facts about A440, but it is important to start to make the connections now between notes on the scale and this Hertz measurement. So if you see a tuning fork or other tone generator, and you see A440, that's what it means. It means 440 Hertz, and it is the standard musical pitch measurement for in the United States and in Europe for symphonies and and any type of music. There are other ranges and other tunings in other cultures, but for the sake of this webinar, we'll stick with Western tunings and Western frequencies. Here's a large chart with a lot of information. We'll take a quick tour through here. Really what I want to point out with this is the gray areas where there's you can see a bass boom is 100 to 250 hertz. And you can see now in the colored lines here, for example, bass in the dark blue, you can see how far down bass goes in terms of hertz. And you go back to this diagram here, the lower pitch now, you can see how that's a low number, 100 hertz, and actually bass goes even lower. And you can see that something like a cymbal or a hi-hat now is way up in 15 to 20 kilohertz range as well. So really working off of this, what the most important thing to know is the lower the hertz, the lower the frequency, the higher the hertz, the higher the frequency. And you can see here that they have a chart running across the top in purple with talking about the intervals between the octaves of C. And we'll talk about that next. We'll go from here into the principle of harmonics. So let's think again about that sine wave that we were listening to. And the sine wave is a pure tone. It's also called, the pure tone is one that is created by a perfect wave. So a tuning fork or a tone generator produces a perfect wave. The perfect wave is a one-tone frequency. It only creates one tone on the frequency spectrum. So let's just review again what a sine waves sound like. That's a pure tone. That's what a tuning fork would generate as well. There is no overtones, there's no harmonics, there's just this one pure tone. But when we start talking about musical instruments, they don't produce just a single tone. They produce not only a fundamental tone, which is the tone with the lowest frequency. So basically the lowest pitch sounding tone. But then also there are overtones that are above the fundamental tone. So anything, a piano, violin, harpsichord, tuba, trumpet, all have both a fundamental tone and overtones. And for the sake of describing music, and once again, this is not so much a scientific measurement as a psychoacoustic term, the combination of the fundamental tone and overtones determines the timbre of the instrument. And that is why the same note that's played on a violin and a clarinet will sound different. So you can perceive, especially if you are a musician, you can tell the difference between a A4 that's played on a guitar and an A4 that is played on a on a trumpet. Same note should, they do correspond, but the overtones and the combination of the fundamental tone and the overtones on these instruments creates different timbres. So that's what timbre is. Here's an example of what's going on. Say, for example, I'm drawing the bow across the string. It's creating a fundamental tone, which you see here on the top, but it's also creating these overtones. The first harmonic, which you see in the middle, you see how those peaks and valleys are different than the fundamental tone, and you can see the second harmonic, and you can see how those peaks and valleys of the sound wave are also different. So think about that bow crossing the string of a violin, creating a note, and the note is comprised of these three waves or more happening simultaneously. So now that we've thought a little bit about fundamental tone and then overtone, we'll move into basically this idea of harmonics, which is another way of calling these overtones, but the overtone with a frequency that is a multiple of the fundamental tone is called a harmonic. Let's look at that a little bit more. So let's think about this. If the fundamental frequency, the fundamental frequency is, say for example, this violin, the first harmonic is 25 hertz. The frequencies of the next harmonics are 50 hertz, 75 hertz, 100 hertz, etc. And this is where the idea of octave comes in. An octave is the interval between one musical pitch and another that is half or double the frequency. So an octave is divided into 7 notes. This once again is for in our system of music, A, B, C, D, E, F, G. Each note that shares the same letter sounds very similar to the others with the same letter because they are multiple of the other's frequency. So let's look at how A progresses here. A1 is 55 hertz. Then the octave up from that A is A2, that's 110 hertz, doubling 55. Go up another octave from A2 to A3, you notice that 110 doubles to 220. Go up from A3 to A4, you notice that 220 doubles to 440. A4 to A5 doubles to 880, and so on and so on. So this is essentially how harmonics are working. Once again, we're using this Hertz measurement, which is frequencies, which is the cycle of vibration, number of cycles per second. And we're seeing here a mathematical explanation of how how a range of octaves works. Here's a chromatic scale which breaks down now that the distance that is between an octave. So we see that that concert A that we talked about earlier, the A at 440 hertz, as it goes up the octave range to the next A, it travels through on the chromatic scale, A sharp, B flat, B, C, C sharp, D flat, D, and you can see how the numbers change and increase as it goes up to the next octave. So all of the notes have corresponding mathematical measurements, hertz. Finally, let's talk about amplitude, which is volume. Amplitude is the degree of change, positive or negative, in atmospheric pressure, the condensation and rarefaction of air molecules caused by sound waves. The sound waves are moving, in this case the air, and sound with greater amplitude will produce greater changes in atmospheric pressure. And here you can see the diagram of air pressure. The rarefaction point with sound waves is where they are low, and the condensation is where they are high. So the degree of change between those two is the amplitude. And here's a little diagram showing now the difference in amplitude between a sound wave um, that is a quieter sound wave. You see there's less of a distance between the baseline and the peak. And then louder, of course, you can see there's a greater distance. And amplitude is measured in decibels. And decibel is essentially a measurement of acoustic intensity. There's a lot of pretty thick mathematical formulas that describe decibels that we won't go into now, but I thought this chart would be helpful in terms of hearing, in terms of rather seeing how, what the decibel levels are of things that we hear in our environment. So you can see moving from soft conversation is 40 decibels to a New York subway, which is 90 decibels, to a medium loud rock concert. I'm not really sure what that really is, but that would be 110 decibels. Only 20 decibels less than the threshold of pain. And you can see here, so you see here the range of decibels. Um, look into further explanations of really the formula behind decibel, but know that decibel is a measurement of acoustic intensity, of the intensity of sound. It's a measurement of the amplitude. So we've gone through a lot of concepts here pretty quickly, so I want to take a little while to summarize here. We talked about sound waves and thinking about a sound wave as a vibration that displaces the particles of a medium. In other words, you pluck the string on the guitar, acoustic guitar we'll imagine, and that string then vibrates the air around it and displaces, the vibration displaces the particles of air. And we talked about the different types of sound waves, sine waves, which are mostly acoustic, which are found in acoustic instruments, and then waves such as square, triangle, and sawtooth, which are found more in synthesizers. And I'll be talking more about the basics of synthesizers in the next webinar next week. Frequency, we saw that the number of cycles of vibration completed by a wave in 1 second is the frequency. And one cycle, one of these cycles equals 1 hertz. And so we learned how hertz is a measurement of frequency. And frequency in terms of musical understanding is referred to as pitch. We then covered harmonics, talking about how an overtone with a frequency that is a multiple of the fundamental tone. In other words, there's the fundamental tone, and then there are overtones, which when they are multiples of that fundamental tone, are a harmonic. And there are other terms for tones that we haven't covered, but it's important to know about at least the idea of a fundamental tone and an overtone and how that relates to harmonics. And an octave is the interval between one musical pitch and another that is half or double the frequency. And we saw that earlier looking at the chart of the different octaves in A, and how each octave has a corresponding measurement in hertz. And then finally, we looked at amplitude, and that's the degree of change in atmospheric pressure caused by sound waves. In other words, the louder the sound, the more air it displaces. And amplitude is measured in a measurement which is called decibels, which, by the way, is named after the inventor Alexander Graham Bell. That was a very quick run through and a lot of really thick concepts of sound, but I hope it gave you at least an understanding of some basic principles which you can then investigate further. But in your music making or in your whatever pursuits you work with in music, you will see these terms, And hopefully this has helped to shed some light um, on these terms and start to at least give you a basic understanding of what these principles mean. So if you have any comments or questions, feel free to contact me, Barrett at dcbclub.com.